In this video, we'll take an overview of the timer counter. As you can see, timer counter consists of 6 episodes and various exercises. In the timer counter overview, I will summarize and explain the timer counter in a table. First, the timer counters 0 and 2 are 8-bit timer counters. The required registers for control are the same. However, the ASSR is different. There are 16-bit timer counters, numbered 1 and 3. The registers for control are the same. The main contents of the timer counter are summarized in a table as follows. Timer counter 0, timer counter 1, timer counter 2. There is a timer counter 3. The structure is 8 bits for timer counter 0 and timer counter 2, respectively. Timer counter 1 and timer counter 3 have a 16-bit structure. The external clock input pins used when operating as a counter are TOSC1 and T1, T2, and T3. The absolute pin number are 19, 31, 32, and 8. The prescaler provides a full prescaler with only the timer counter 0. As you can see, there are 1, 8, 32, 62, 64, 128, 256, 1024. Timer counter 2 will be 1, 8, 64, 256, 1024, like timer counters 1 and 3. So, please understand that timer counter 2 is an 8-bit timer counter. But it is the same type of 16-bit timer counter prescaler. There are various registers for control like this. There are various registers for control like this. Please note here that only timer counter 0 has an ASSR and timer counter 2 does not have an ASSR. Control input pins include the following. Output pins include OC0, OC1A, OC1B, and OC1C as output comparison matches. However, timer counter 2 has an output pin OC2, which is designed to be the same pin as OC1C. Please be aware that if you output 2 waveforms simultaneously, you can get a modulated waveform. The interrupt services are as follows. You should know that there are overflow and output comparison matches. There are 3 output comparison matches. In timer counter 1, he said he had OC1A, B, and C. There are A, B, and C. I hope you know. As a feature, timer counter 0 is RTC capable. It is a timer designed to enable real-time clocking. I said that timer counter 0 can be used with any prescaler. Therefore, there are types of prescalers like this. Capture is possible. And the 16-bit timer counter using ICR1 and ICR3 can directly record the top value by designing it to be the optimal value for hardware control. So you can practice this when controlling servo motors. Please know that we can set the optimal control values. This diagram will be a control element that enables the highest level interrupt service by enabling global interrupts first. Next, write 0x01 to the register called TIMSK to activate the overflow timer counter. Next, in the TCCR0 register, you can set normal, CTC, EWM, etc. as the prescaler and output comparison match mode, and which pin to use as the output pin must be decided by the I/O output. So, you should know that the control elements are set from detail to global. This time, let's look at the block diagram of timer counters 0 and 2. It's like this. It is a 10-bit prescaler with a maximum value of 1024. Yes. When the timer is cleared in a comparison match, it is automatically reloaded. As you can see, the clock connected to the terminal is 32.768 kHz and is connected to the TOSC1 and TOSC2 pins. 2 interrupt sources are provided, and as you can see, an overflow interrupt and an interrupt for a compare match can be created. As you can see here, I've given it a star. The overflow interruption can be created in C code like this. And the comparison match output and comparison match interrupt can be created like this. So C language code like this can be created. This code was created by Code Vision AVR. This interface is also taken from Code Wizard AVR. If you briefly look at the block diagram, the control logic is controlled by TCCR. Determining the count value, clear value, and direction are done. By making this decision, we can compare the TCNT value and the OCR value to see if they match each other, and generate an output comparison match interrupt, or generate a waveform. Generating an output waveform is used when controlling a PWM waveform, such as a speaker or motor. Then, as you can see, the clocks that affect the control logic are 32.768 kHz and 16 MHz. And when each is input, it is divided into the first prescaling through XDIV. In the prescaler, the period can be fully optimized for the hardware, thus influencing the control logic. Finally, if we write 1 to the AS0 bit of ASSR, we can use RDC in asynchronous mode, using 32.768 kHz as the clock. A real-time clock can be used. Please be aware. Also, as you can see, the OC0 output becomes PWM in phase-correct PWM, CTC mode or fast PWM. Through this PWM, we can control speakers or motors. Now, I have explained the block diagram for timer counter 0. Timer counter 2 is similar to this, but only the clock part. Here follows the clock part of timer counter 1. So this diagram was a block diagram for timer counter 0. It was a block diagram. Let's take a look at the features of timer counters 1 and 3. As a timer, for the 16-bit up/down counter, various modes are provided. You can check out the various modes later in the control exercise. You can also see that 15 different modes are provided in the Code Wizard AVR interface. At timer counter 1 provides a 10-bit prescaler. The maximum value is 1024. 3 independent output compare and match units are provided. OCXA, OCXB, OCXC. So 1 or 3 will be applied to X. Therefore, 6 output comparison matches are provided. We said that 1 input capture unit is provided for each timer. It is provided for T1 and T3, respectively. A canceller is provided for input capture noise. Automatic reloading when the timer is cleared in a comparison match is equivalent to a timer counter of 0. It is possible to generate PWM by eliminating glitches in the PWM waveform. Various PWM output waveforms for 10 outputs are provided. Additionally, 10 independent interrupt sources are provided, with 5 for timer counter 1 and 5 for timer counter 3. So, as you can see here, the external outputs are OC3A, 3B, and 3C. There is OC1C. Here, OC1C is designed on the same pin as OC2, on pin 17. It can be modulated. Please know that if the simultaneous output occurs, it will be modulated. This time, we will look at the block diagram for timer counters 1 and 3. The internal clock is used as a clock. And, as you can see here, TX can be used by using the clock input through numbers 1 and 3, as the clock passes through the prescaler. OC ABC output pins are provided for each external output pin. By calculating the optimal control, we can record the ICR value directly and use it to set the top value. So if you look at the block diagram, the control logic is as you can see. You can use a 16 MHz clock, and you can use it in control logic by accepting the external clock coming into the TX through an edge detector, and then applying a prescaler. There is a timer counter. And, because 3 output comparison matches occur, there are 3 OCR ABCs. Like this. Each OCR has an output pin that can generate an external output waveform. OCR, A, B, and C are output. As you can see, we set the mode and output ABC according to the output mode determined in the mode. And most importantly, as you can see, the ICR register for the optimal hardware directly here in the input capture. By writing this value, you can have an effect right here. The control logic will be executed by influencing the ICR register. This concludes the block diagram explanation of timer counters 1 and 3. This time, we will look at the characteristics and symbols of the timer counter. The characteristic of the timer counter is that if the clock source is not selected, the timer counter stops. Additionally, OCR, the output comparison register, always compares with the TCNT value. If a match occurs, PWM output is executed, or frequency change output is made through the OC pin. This will all be done based on the comparison results. When looking at terminology related to timer counters, the term count means increment or decrement. It increases or decreases by 1. About what? By timer overflow or compare match. This value is applied to TCNT and is determined according to the register setting result. There are up and down directions. Up is an increment and down is a decrease. Clear means the TCNT value is recorded as 0. So this means that all bits are recorded as 0. CLK refers to the clock of the timer counter. Bottom. The minimum value. The minimum value that a timer can have is 0x00. Max will be the maximum value that the timer counter can have. For an 8-bit timer counter, it is 0xFF and is a hexadecimal number. In decimal, it would be 255. A 16-bit timer counter would be 0xFFFF in hexadecimal. In decimal, it would be 65,535. Top value means the maximum value that the timer counter can have while the counter is running. According to the set operation mode, the 8-bit timer counter is 0xFF. But in CTC mode, the value set in OCR 0 becomes the top value. The 16-bit timer counter is 0xFFFF. In CTC mode, this will be the value set in OCRNA. When we determine the optimal resolution such as ICR1 or ICR3, that value can become the top value. It can be a top value of 16 bits. So I marked the ICR value with an asterisk. So it is the optimal value. Please be aware that the ICR register sets the top value to the optimal value according to the hardware. We use the following picture to understand the timer counter. Go up and down by taking the virtual mountain height from 0m to 65535m. It uses the concept of mountain climbing, where you go up to 1023, go down, then go up to 255 meters, and then go straight down. Using this, we will easily understand the microprocessor's period and PWM waveform. So far, we have looked at an overview of timer counters. Thank you.